A little part of me is afraid to start this video, one, because I just messed it up the first time I tried it, and two, because it's such a serious topic that we need throughout the year. The cross product, or also known as the vector product, is vital to this class. We will use it all year long in the same way that the dot product is one way to multiply. The cross product is another way to multiply vectors. There are some limitations, though. The first is that a cross product has to occur in 3D. It does not exist in 2D in the same way because I can't overlay my unit vectors. And notice, this produces a vector quantity, not a scalar quantity. One of the many things that's different between these two. Also, this one takes a little bit longer to calculate, so let's look at how this is set up. These are my unit vectors, I, j, k. Remember, this is the x, y, and z directions in their most basic 1, 0, 0 forms, right? I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. All right, so I lay those over the top. I put my A components, x aligned with x, y aligned with y, z aligned with z, and for the b as well. And then I'm taking mini determinants. When I'm taking that I component determinant, it's the determinant of the 2 by 2 underneath it. The j component, it's the determinant of the 2 by 2 underneath, and the k is going to be the 2 by 2 left over. And also, don't forget, one of the easiest, biggest places that I know students will make mistakes on this lesson is this negative. It just gets flipped. This negative, it just gets flipped. All right. Let's try one. And I'm going to lay down my A and B components. Now, it's just time to calculate that cross. And again, I'm taking my I component and doing that times this little 2 by 2. My j component times this little 2 by 2. My k component times this little 2. Go. Negative 14 minus 24. 21 minus 16, negative 18 minus 8, and again, simplifying down, makes negative 38i, negative 5j, and negative 26k. And again, I can turn this into a vector if I needed to or wanted to, if it was somehow more useful for me this way. And that's how I find the cross product. Now, this new vector I've found, let's call it C. C has some special properties. First and foremost, if A and B are out here, let me move back my camera for a moment. If A and B are these vectors sitting on the desk, C would make a right angle with them. In case you can't tell, C is standing straight up. So I have a right angle here. I have a right angle here. That's called orthogonal. That's what it says on the next line. The vector produced by A cross B is orthogonal to both A and B. And you're thinking, how could one thing make a right angle with two different things? The only way it makes sense is 3D. Right? For one vector to make a right angle with two different vectors in two different directions, it only makes sense if it's in 3D. And actually, if I'm being honest, there's another vector coming out of the bottom of this table headed in the same but negative direction as green that's also orthogonal. And so part of what we need to do is we need to check, hey, when I find that orthogonal vector, is it coming up out of the page or down into the page? And that's what this next section is. First, let's draw that little triad, because this is a very classic, common look that I would have vector A here, vector B there, and then vector C would be coming out of it, making a right angle with both A and B. Looks a little bit silly when you draw it in 2D, but I promise you that if I did C dot A, I should get 0. And if I did C dot B, I should also get 0. Because when I dot two things that are orthogonal, they come back and get 0. And you can check those if you don't believe me. Let's continue on, folks. Let's look at this idea of orthogonal, and let's figure out this right-hand rule. The right-hand rule lets us understand whether that resulting vector comes into or out of the page. I'm going to draw A here and B there. And unlike me, you should double check that you use your right hand when you do this, because I did this wrong in the last video. If A comes first, I lay my hand along A. I sweep my fingers towards B, and you can see my thumb is sticking up. And that means that resulting vector is coming out of the page. Whereas if I took that same exact situation and orientation to lay my right hand across B, to be able to sweep it towards A, my thumb is pointing down. Let me zoom out a little bit so you can see that one. Right? If I tried to lay my hand this way and sweep B to A, I'm not sweeping from B to A. I'm sweeping from B to nothing. If I want to sweep from B to A, you see that my thumb has to go in for B to sweep towards A. And that's how I know if that resulting cross product is going into or out of the page, a very important concept. There. And again, orthogonal. In case we didn't write this down, this is right angle. 90 degrees. Now down here I have a very important fact. And it's not so much that I'm going to prove it today, but gosh, this is useful in about every proof that involves a cross product. This shows up. I don't have the time or the energy to prove that it's true, but I can put about as many stars as I possibly could next to it. And notice, this isn't the cross by itself. This is the magnitude of the cross is equal to these magnitudes, individual, times the sign. Well, wait a second. That means these have a sign relationship. Right? Dot products had a cosine relationship. That means these have a sine relationship. That means they're maximized when they're perpendicular. So a sine or a cross product is kind of measuring how dissimilar are these. How far apart are these vectors? How opposite are these directions naturally, because the angle between would then be maximized in that sine range. Remember, cosine or dot product was how similar they are, how much in the same direction they went, when this is almost doing the opposite. How opposite are they? How far in the opposite directions? How perpendicular are these? So I don't know if you want to go back up here and just remind yourself this is a sine relationship, but it does matter. And we'll carry this concept all the way to fourth quarter, that cross products are a sine relationship and measure how different things are, where cosine is dot product, how similar things are. And so let's use this idea. Notice this proof has a very bizarre English language math thing. That is not a typo. This means if and only if. What this means is not only does P imply Q, our first statement imply the second, if two are parallel, then their cross is 0, but then you would say the opposite. If the cross is 0, then two are parallel. That's what that IFF means. And it's important that if I'm going to prove these two things, I have two proofs to make. First, I say, if they're parallel, show me the angle between is 0. Show me that cross is 0. Okay, let's do it. If these are parallel, then the angle between has to be 0. They have to be headed in the same direction. Well, if the angle between is 0, then this calculation from that formula we learned on the back side has to be 0 because the sine of 0 is 0. Well, we know that this has to be equal to the cross product. If the magnitude of the cross product is 0, the only answer is that A cross B is 0. There's no other way a magnitude would be 0 unless the cross was 0. Then in the other direction, starting with this, if A cross B was 0, well, if A cross B was 0, then we're building that proof in the opposite direction. Then the magnitude of A cross B is 0. And if the magnitude of A cross B is 0, that means A times B times sine theta is also 0. And yeah, the zero product property is going to set up two cases. It's going to say either A, magnitude of A is 0, magnitude of B is 0. This case, there's a little bit more to it that's not worth talking about, but obviously we're not going to be doing this with the 0 vector, right? The vector that's 0, 0, 0, which is technically parallel to every vector. Not worth talking about. We're just focusing on this case that says, hey, if sine is 0, then the angle between is either 0 or 180. And that means they're parallel. Okay, a couple more things to talk about here as we burn through the second half of this page. Let's revisit that parallelogram that we had from Intro to Vectors in 12.2. Not the same exact vector, but I think it honestly is a multiple of it. This is my vector A. This is my vector B. Remember, when it says sketch the area spanned by, it's saying create the parallelogram. Remember last time how challenging it was to find this area, or that I just completely left it off because it was too much? Well, now we can do it with this proof, with this concept, where again the formula that for cross product, A times the magnitude of A times the magnitude of B times sine theta. Let's see how that comes into play here. Because again, the area of a parallelogram is base times height. I know my base here is B. So then my height, well, imagine I can use trig here. Sine of theta is OH. Opposite and hypotenuse. In this case, the opposite is the height we're looking for, and the hypotenuse is that magnitude of A. And so if I need the height for this area calculation, I would just say that the height is equal to the magnitude of A times sine theta. And so all of a sudden, if I put this together, you'll see what happens. Area is magnitude of A, magnitude of B, sine theta. Well, wouldn't you know, that's also the magnitude of the cross product. Incredibly powerful, incredibly important and useful. Just this concept of, hey, I can cross them, take the magnitude, and that gives me the area of the space they span. So somehow, by crossing up the x's and the y's, I find and the z's, I find the area of the 2D space they span. Again, like if I drew that imaginary, if I drew this imaginary parallelogram up here, this cross product, this value finds that base times height area. Wild. And it's all because of this formula down here. And in this case, if I wanted to finish this problem, all I would have to do is add a little z to it, right? Because cross products can only exist in 3D. So to do a 2D to 3D mapping, just set z equal to 0. And it'll still find that area just with z equal to 0. So these vectors become 1, 4, 0 cross 3, 1, 0. And if I took that magnitude, I would get the area. You should be able to get a really nice clean number out of this. Double check it with me. But I got 11. All right, and those zeros make that cross product go much quicker because you end up with a lot of zero multiplications. So on this next one, it says find the area of the triangle with these vertices. Oh, would you look at this? I'm going to have a triangle that looks like this. A, B, C. Well, isn't the triangle just really half of a parallelogram? Like if I added these vectors together, I would end up here, and subtracted them, I would end up there. So really, I could do this same calculation and just cut it in half. I do have to kind of turn everything into vectors, right, instead of just coordinates. So I would take vector AB, which is negative 15, 3, negative 3. I would take vector AC, which is negative 13, 12, negative 7. I would cross them, and I would get to my answer. In this case, it's not a very nice answer, but that idea would still hold true. You would get some large number, but I assure you it would work out. And yeah, I end up with some really ugly cross, but I promise when you take this magnitude, and again, I need to take half of it, so the area is going to be 1/2 of the magnitude of this AB cross AC, where I end up with 75.02. Again, a case that a calculator would probably be your friend, a case that a test question would probably be nicer than this one. Towards the end, just revisiting this right-hand rule and trying to make sense of it. Again, doing your best to kind of draw this or use some kind of axis. But these are helpful and informative. The fact that, again, when I have I and I'm crossing to J, I end up with positive K. But if I were to cross the other way, Y to X, I would end up with negative K. I, but K cross J would net me negative I. K cross I would give me J, but I cross K would give me negative J. So kind of that forwards, backwards, positive, negative idea, but also realize these are not nice calculations. Cross products are not commutative and are not associative, despite my typo there. They're just not going to work out nicely, and you can see it immediately here. Right? I cross K would give me negative J. But if I switch these groupings around, I cross I would give me 0, which would not give me negative J. And the same thing over here, I cross I gives me 0, which gives me not negative J, but 0. They're not commutative. I can't just flip these around. And you can even see, that means A cross B is not the same as B cross A. You end up with a similar answer, but the direction changes because of that right-hand rule sticking out of the page or going into the page. Last but not least, a couple of things that this can do for us is that it can help us tighten bolts in the real world or loosen bolts in the real world. Again, if I were to kind of draw this picture for you, I have my little wrench. It's working on a bolt here. That bolt is headed this direction. I have my radius here along the handle of the wrench, and I'm applying some kind of force down this way. There's some kind of angle that I'm applying that force, and again, we know that that force is maximized when it's working perpendicular rather than in the same direction as the wrench. If I was pulling it in the same direction of the wrench, it wouldn't be turning the bolt at all, but if I can wrench it perpendicular, that's maximizing the force, or in this case, maximizing the cross product here. It'd be helpful to know that torque is the same as R cross F. In this case, since I don't have vectors for either of these, I do have their magnitudes. So in this case, I can just go magnitude R times magnitude F times sine theta, and it will tell me the amount of torque being applied to that bolt way down here. 0.3 times 40 times sine of 60. 0.3 times 40, that's rad 3 over 2, and I would get 10.39. Alright, the triple product is where we're going to kind of leave off, and this extends into our next lesson that has to do with the equation of planes. And you might not see it when you first get there, but this idea is that if I have that third vector, it's going to apply this space in that third dimension. Again, a product is I multiply. In this case, this is going to give me an area, and this is going to give me a direction. All right. So again, to go back to that A, B. Well, again, when I cross them, it will essentially find the area of this parallelogram. But again, it shoots off that C vector in a direction. Again, in this case, A cross B, I think it should be going down. Catch myself before I have to re-record the whole video. A cross B, this thing should be going down. And then this whole thing gets cosigned, gets applied. Again, this is saying how much of this is headed in that direction. So what I end up generating is what's called a parallelepiped, spanned by three vectors. I'm finding a volume of a shape because I'm taking this parallelogram and applying it in that cross product C direction. And this also is a fun little note that I threw on here. If the volume is 0, that means all these things are coplanar or exist on the same sheet. And I'll just leave you with that thought. Having all of these in the same sheet, what does that mean for an infinite sheet that carries on forever? How could I take a direction and an area and apply that forever? And the fact that the volume would be 0 shows up in those 12.5 notes. If I have three vectors and it wants me to find the volume of the parallelepiped, yeah, cross it, dot it, Because again, this cross will come out with a vector. It'll be a vector dot a vector, and I know what comes out is a scalar number that would be that volume. That's enough talking. That was a long one. I hope this was a good introduction to cross product.